Hello and welcome back to the video lecture series on statistics for machine learning. This is Amit Kumar Das. So we have already understood the definition of probability, right? The classical definition of probability. Now let's try to understand a few theorems which are very important in context of the probability, right? The first and foremost theorem is basically when there are two events, A and B, okay? And when it's a general event, okay, so we can say that P of A plus B, so probability of the events A and B, okay, uh, A or B rather, is the probability of A plus the probability of B minus the probability of A B overlapped, so occurring together. So I mean, if I just map the outcomes of the events A and B. I mean, I'm sure you have, many of you or most of you have already seen this thing. This is called a simple Venn diagram in the set theory, right? So if the outcomes of A are being shown as a part of this circle A, and the outcomes which are common to B are shown as this ones, right? This B. Uh, Now, the probability of A or B, so either A or B, right? This total probability is basically the probability of A, this whole thing, plus the probability of B, this whole thing, minus, since there is an overlapping portion here, right? There's an overlapping portion here where both A and B has occurred. If we don't assume A and B to be mutually exclusive, okay, in that case, we have to subtract that portion, that overlapping portion probability because of that, okay? So that is P of A minus B. In case we are assuming that they are non-overlapping or mutually exclusive, so something of this sort, so A and B do not have any outcome in common, right? So obviously there is nothing in the AB, this A intersection B from the set theoretic perspective. There is nothing there, right? So we can just assume that P of A plus B is equal to PA plus PB when A and B are mutually exclusive. Now, when we think about A and B to be complementary, right? So basically we replace this B by A complement. Then, and A and B are basically mutually exclusive. Obviously, when they are complement, they are going to be mutually exclusive. There is nothing to say about that. So exhaustive as well as mutually exclusive. Then we can say that P of A plus B, P of A plus P of A complement is equal to 1, right? I mean, in the last session, we have already talked about it, right? P of A plus P of B is equal to 1 when A and B are mutually exclusive as well as exhaustive. So when A and B are complementary, obviously they are mutually exclusive and obviously they are exhaustive, right? So that's why PA plus PA complement is equal to 1. So that's another theorem. Next theorem, very important theorem. This is also called theorem of conditional probability, right? So what is the theorem? P of AB. So we got an AB here, right? P of AB. What is P of AB? How can we find that out? P of A, so probability of event A plus probability of B given A. Okay, this is called given. So probability of B when we know the probability of A, okay, has occurred. So in this case, we are now like shifting from the a priori or the classical definition to a conditional definition where the occurrence of event A will have a bearing on the probability of occurrence of event A will have a bearing on that of probability of occurrence of event B, right? It can also be stated as P of B into multiplied by P of A given B. So probability of event A given that event B has already occurred. I'm not going to get into details of it because it's going to be a little, intense. So I'm not going to get into details of it. Uh, Quite following this one is P of A B is equal to P of A into B when A and B are independent events, when there is no dependency. So P of A given B, there is no dependency of A on B or B on A, when they are completely independent events. In that case, we can say that P of AB is equal to P of A into P of B. Okay. Uh, Following this conditional probability, what we can also derive is something which is extremely important in context of machine learning, which is the Bayes theorem, right? Uh, we have certain machine learning algorithms like the naive Bayes algorithm, right, which follows the Bayes theorem. What is the Bayes theorem? What does the Bayes theorem state? Probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. Now, if you just look at it, it is nothing but if it basically implies probability of A given B multiplied by probability of B is equal to probability of B given A, B given A, okay, given A multiplied by probability of A. Now, obviously, this is true because this one is equal to P of AB. We have already seen that from the prior definition. This is P of AB, and this is also P of AB. P of AB. Okay, so obviously this is going to happen. This is just a rearrangement of this whole thing. This whole thing. It's just a rearrangement, right? P of A into P of B given A, okay, is equal to P of B into P of A given B. So that's rearranged gives us the Bayes theorem that P of A given B is equal to P of B into P of A divided by P of B. Okay, so this is the Bayes theorem of probability, conditional probability, which is used very often when we do the machine learning algorithms, right? So these are the primary, and these theorems, I mean, you can refer to any standard book on statistics. You can you can get the proof of each and every of these theorems. This is very straightforward. There are very straightforward proofs. Also, very simple proofs using the set theory, right? But I'm not going to get into that because our objective is completely different. We just want to get a basic hang of the different theorems of probability, right? So now that we have covered some fundamentals of probability and also the theorems of probability, I'm going to cover a very important portion in the next couple of lectures, which is the concept of uh, probability distributions. Okay, so let's cover that as a part of next couple of sessions. Okay, so stay tuned. Thank you very much.